All right, let's get started. Thank you so much for joining us for another HRAI webinar. Today, we're discussing decarbonizing domestic hot water systems, reducing GHGs with high-efficiency heat pumps. And to do that, we've got two folks from Mitsubishi Electric Sales Canada, Inc. We're going to take us through the details, Rizwan and Tyler, who I'm going to introduce in a second. Now, this is a packed presentation, so we're going to hold questions towards the end. If you'd like to ask yours, you can find a Q&A button at the bottom of your screen. Put them there. We're going to get to as many as we can. Also, this is being taped, and you can watch it on HRAI's YouTube channel after the fact. So without further ado, I want to invite Rizwan and Tyler to introduce themselves so we can get this started. There's one of them. There's Tyler.
Okay, quick test for mic and audio and video.
Loud and clear. Thank you so much for joining us.
Okay.
And you're going to be, oh, there we go, two of them. So I'm going to back away and let you guys do your thing. I'll be here at the end of the presentation to take questions.
Sounds good. Thank you, Matthew. Okay, so good afternoon, everyone, and welcome to today's webinar hosted by HRAI and Mitsubishi Electric Sales Canada. My name is Tyler Pullen, and I'm a product manager for applied products at Mitsubishi Electric here in Canada. I'm joined by my colleague Rizwan, as you just saw. He is our applied sales manager for the Canadian region also. And together, Rizwan and I support the product application, industry education, and on-the-ground implementation of a wide range of air-to-water heat pump technologies offered by Mitsubishi Electric. Thank you for joining us today as we take a closer look at the decarbonization of hot water systems using heat pumps. We know our audience today includes HVAC professionals with a range of experience in domestic hot water heating technologies. And while traditional approaches are well understood, integrating heat pump technology for domestic hot water is still an evolving practice in our industry, especially as decarbonization and sustainability remain top priorities. Our objective this afternoon is to share actionable design guidance, control integration strategies, and key performance considerations for heat pump-based domestic hot water systems. So I will now share my screen. Matthew, how are we doing there? Good?
Good to go. Yep. Thank you.
All right. Okay. So before we get started, here's how Rizwan and I will cover today's agenda. Rizwan will begin with answering the question of why decarbonizing hot water systems matters, looking at energy use, sustainability goals, and what's driving changes in our industry. He'll also cover design fundamentals, including system types, storage, sizing, and how hybrid options can fit into different applications. Next, I'll guide us through the technology portion, explaining how heat pump water heating systems work, why CO2 is an ideal refrigerant, and what sets this approach apart. We'll then look at effective system integration, covering controls, piping, storage, tank design, and temperature maintenance to ensure reliable daily performance. We'll also touch on installation, maintenance tips, common mistakes to avoid in the field, and best practices for cold climates. By the end of our session here today, we hope you'll have a solid understanding of how a CO2 heat pump water heater supports decarbonization and the key successful steps that need to be taken for successful application. And with that, I will hand it over to Rizwan, and he will get us started. Rizwan, take it away.
Hi everyone, Rizwan Faruqi from Mitsubishi Electric Sales Canada. I'm the sales manager for the applied sales products and especially for air to water products for heating applications. So first I will start why we are doing this decarbonization and what drives that decarbonization controls in terms of first thing like the efficiency. So obviously you are looking for the equipment, those are more efficient to reduce the energy consumptions. But you can see, especially in the high energy consumption area of comfort heating and cooling, there's not much improvement in last 10, 15 years. We hardly gain some few points in terms of efficiency improvements. The next thing we always looking for renewable energy resources from the like solar, wind, hydro, or even nuclear or some other resources to reduce the carbon emission effect. And the last thing, mostly we are trying in most of the application that reduce your natural gas consumption or reduce the consumption of the fuel at the site. And by doing that, they are adopting electric equipment or furnaces, heater, and everything. So we just want to reduce the more electricity in the building in place of burning fuels inside the buildings to reduce the emission on the sites. And as I said, that renewable electric heaters are the second options in place of the gas furnaces, especially in the single home heating applications, whether you are doing domestic heating or water heater. The other thing like electric heat pump. So why heat pump? That as compared to any electric heater, at any point of the time, you will find that electric heat pump is more efficient in terms of the electric condition, and you'll get better efficiencies. So you provide 1 kilowatt energy to the heat pump, and in return, you will get 2, 3, or even 4 kilowatt as compared to any gas or electric heater, where maximum you can maximize up to 1 kilowatt against 1 kilowatt. So in terms of renewables, we have solar, wind, or other storage option to find our energy resource sources. Let's talk about the water, especially in the residential building, what the heating consumption or energy consumption, especially for heating the water. So from a Natural Resource Canada recent study in 2013, that average Canadian is consuming 75 liters of hot water each day, and obviously that goes to for your clothing, cleaning, dishwashing, bathing, and all the needs. But overall, it's 20% energy consumed for just only heating the water for your daily usage. So that's the amount of energy you can see we are consuming continuously. And it's not like that heating or cooling, which is seasonal. That is something you need all around the year. That's why it's a huge amount of energy. Whether you are a single home, hospital, hotel, or healthcare, everywhere there is a need for hot water. So how the hot water profile or hot water needs looks like. The rate of consumption for domestic hot waters varies dramatically. It's not like the heating and cooling that you have a worst scenario at a peak either in the summer or winter. It's all depend on the multitude factor of including like the nature of building. So it could be a residential building, it's a different consumption. If you have a hotel, it will have different consumption. So maybe a same 10-story building, and because of the nature of the building, you will have different consumption or different requirement for the hot water. Then obviously the second thing comes the quantity and the type of fixture. Obviously, if it's a hotel or hospital, you have a different number of or quantity of the fixture requirements as compared to a residential or home. And the last and the most important thing is the behavior of the occupant. That's all like very important to educate all the people for energy conservation and reducing any type of energy, either for comfort heating or cooling, or here for domestic hot water or hot water usage. So in the all building typologies have domestic hot water demands that like fluctuate between times of the peak draw and lower years. So you have a peak draw maybe morning and evening when all the people are inside, or you are taking bath, or you're coming from the work. So you have a peak time, and in between there is the time that will be low demand, and the system can reproduce or store the water. Most building type do not experience seasonal change, so we will have like continuous demand or similar demand all around the year, except where you have a seasonal, maybe a seasonal hotel as a resort or something. There maybe in the summer or winter time you have more occupancy, and because of that your demand will change. So the graph below just show that how the system is producing the hot water. Your storage capacity is varying as the consumption goes up and down, but it continuously meeting the demand. So in terms of, we have like two terminologies used for recovery and storage capacity. So domestic hot water must respond to constantly fluctuating loads, and their sizing must be considered as a blend of two basic factors. The number one is recovery rate. So that's the like your generation capacity or production capacity of the equipment. So that the amount of hot water that a domestic hot water can continually produce as a specified temperature rise. That could be in liter of hours or gallons of hour per day per person. So that's your recovery rate. The second thing, which comes always, the storage volume. So the volume of the domestic hot water can be accumulated and stored at a specific temperature. Generally, it's like 140 degree Fahrenheit for the city requirements. And once we are supplying to the building, it's 120 degree Fahrenheit to avoid any scalding or burns. A specific building demand for domestic hot water can potentially be met by a range of these two parameters. Like we have two types of system. Either it could be a low recovery, high storage. So in that system, with high volume of storage and low rate of recovery, may be able to satisfy a relatively large hot water draw volume over a short period of time. As long as this is followed by a period of reduced demand, that allows the system to slowly recover its stored volume back to temperature. So you have a high demand for a short period of time. So instead of sizing your equipment for that high demand, you can size the equipment a little bit lesser capacity and then compensate with that peak from a supply from a storage. So in terms of high recovery, you have that reverse criteria. So you have a very large equipment or large capacity equipment for producing the hot water, but you will reduce the storage. It could be a instantaneous system for a smaller application where you can afford it, or it will be more feasible to have that kind of system. The two graph below show the extract from HRAI handbook, that how you, for different type of building, if you increase the recovery capacity, you can reduce the storage volume, or vice versa. If you increase the storage capacity, you can reduce the recovery rate for the equipment you are using. Let's talk about something, the conventional recovery based domestic hot water system, especially for large gas boilers we have in most of the old buildings. So that will have very high relative recovery rate due to the use of high temperature combustion. So previously, if we have a gas heater inside the building, there is no problem. That same 1-inch or 2-inch gas supply can provide unlimited amount of gas, and you can size your equipment based to your burner capacity. So that was not a problem. But if you have you will replace that system with an electric boiler or something. Now you have to, most probably, especially in the existing building, you have to have some infrastructure improvement for the supply of that much power supply. The heating output and efficiency are not affected by the ambient temperature. So both the electric and gas boiler, as compared to a heat pump, they are not affected by the outdoor temperature. But if we have a hot water heat pump, its capacity will vary from the outdoor temperature. The advantage we have with that, the older system, that lower thermal efficiency due to the energy transfer losses associated with the combustion product. And the last thing, very high operational greenhouse gas emission with that natural gas combustion on the site. So in terms of the design guide, we have like a few resources are available. One of them, this American Society of Plumbing Engineers. Generally, they use that either 30/3 or 5 minutes peak demand terminologies. So according to the 33 guidelines on the side, is based on the building peak 30-minute demand, and your storage volume is based on 3-hour maximum demand. So your equipment should be sized that it can meet the 30-minute demand, and your storage both together supply the hot water for both 30 and 3-hour demand. The next thing we have from HRAI handbook, the chapter 51, that give you the guidelines, especially for sizing the domestic hot waters and how it rates the low, medium, and high the type of building, the occupancy of the building, all those factors are connected, and then you can find out that what's your gallons per hour per day of domestic hot water is needed. So especially if you have a single refrigerant-based domestic hot water heater, so to reduce the first cost, you would like to have a smallest size of heat pump that will benefit from a greater ratio of storage tank capacity per unit of energy input, and for conventional water heater as compared to conventional water heater. And in that case, your hot water heat pump system designer generally uses the smallest capacity possible with the consistent with the annual energy average of 12 to 18 hours, or maybe more running time combined for that system. So you will have a small storage system, but high storage and low capacity, and that low capacity system will be running for a longer period of time as compared to that 30 or 3-hour demand. So that's the, I think, picture tell you the whole story, the 1,000 word. So on the left side, you get the traditional fossil fuel system like a gas boiler. You have a higher capacity of 350 kilowatt and only storage with 360 gallon for it. And the same building, if you want to replace with a heat pump, as I mentioned previous slide, that we want to reduce the capacity as much as possible to reduce the initial cost. So, but by doing that, you have to have higher storage capacity. So that capacity from 360 gallon, now it increased to 18 or 1900 gallons, almost 3 or 4 times more. So that's how you will design the new system if you want to use your hot heat pump as a water heater. That's the one advantage also that, so if you can use the lower capacity or lowest capacity required for the hot water heat pump, especially in the existing building, you don't need to upgrade your electricals installation or any infrastructure. That will be a big cost, especially if you are looking for all electric heating. In terms of different criteria we have for domestic hot water consumption per person, from the HRAI medium says that for the medium range, like for per person per day, you will require 49 gallons. Ecotope, that's an online tool available. They recommend if you have a low fixture, which is like 1.4 or 1.5 GPM for your faucet and shower heads, then you can use 25 gallons per day per person. And HRAI low criteria is based on if you have all those energy saving measures, then you can use the criteria of 20 gallons per day. So you can see that how much the gallons per day varies because of different criteria. There's one more reference comes from City of Vancouver study recently done for different type of building. That's the actual consumption of those buildings. And they say that could be as low as possible up to 16 gallons per day per person. So those are different criteria. You have to find that which type of building you have, how much is the occupancy, what's the type of fixture, and all this together, and find the best possible number for your design. In terms of sizing your domestic hot water heat pump, there is a one online tool is available. That is an educational tool and give you all the guidelines that how you design your system. That's a really good tool. I have that link on the top, that ecotope.com. If you need more detail about it and learn more to use this tool, that's a good tool available online for sizing your system, especially for hot water heat pump equipment. Generally, if you go on the side, you will see that you can provide the input of the building load, that how many people or the occupancy, like number of apartments, what criteria you want to use. So in this case, I use 49 gallons per day, but as per your design, you can use either HRAI low or City of Vancouver guideline, or if you have existing building. So that will change your total gallons per hour per day and the capacity as per the design. So generally, our storage is 140 degrees Fahrenheit, just to avoid the Legionella problem, and 120 degrees supply. This is all standard in most of the design in all city or municipalities. So with all those information, you will get the heating capacity requirements. So here, like 260,000 BTUs per hour, that's the size of the equipment you require. But remember that if you are sizing a heat pump, size your heat pump at the lowest design temperature of your area. Let's say if I'm in like minus 18 or minus 20 degrees Celsius, so your heat pump can deliver this capacity. And the last thing here is the resistance heater for the swing tank. So that is also provided for 9.3 kilowatt and both the tank size. The graph on the left, that is the trade-off between your storage capacity and the production capacity. So as I mentioned that if you're designing, you can compromise on that one and find out that where is your sweetest spot in terms of energy and both cost saving. So if I increase my storage capacity to instead of having 1400 gallons, if I have 2000 gallon, then my production capacity or the heating capacity of the equipment will reduce to only 200,000 BTU. But if I don't have a space, then maybe I want to go less storage capacity of 800 gallons. And in that case, I will end up like 350 BTUs per hour for the equipment sizing. So that's how you can play with that graph and find out which the best solution available for your design. So in terms of the equipment available, we have like two types of equipment. Either you can have a multi-pass system or a single pass system. So generally that is single pass system is low GWP refrigerant, CO2 system, which can provide you very high delta T. So if city water is coming at 40 or 50 degrees Fahrenheit, it can raise the temperature from 40 to directly to 140 degrees Fahrenheit. If you have a low GWP system like any 454B or 454C most probably, then you use a multi-pass system which can continuously reduce, increasing the hot water temperature in the storage tank with a low delta T of 10 to 15 or 20 degree Fahrenheit maximum. You will find that. So these are the two options available in terms of today Tyler will most be emphasizing on the CO2 refrigerant system that provides a higher delta T, better efficiency. So if we see the different type of equipment we are using in for like electric boiler, conventional boiler, and their efficiency. So if you have an electric boiler, we can assume that it can provide up to 100% efficiency or COP of 1. If you have natural gas, it will be depending on what type of system or natural gas you have. It can be ranged between 90, 95 for a condensing boiler. But if you have a heat pump, that can range from 2 to 4 or even better if you have a 4-pipe system or something. So even like it can provide much more than 4. But on the average, most of the hot water heat pump system, they'll be working between 2 to 4 range. Normally, if you are going below minus 15, they will be like 1.5 or something, but it will be 40 for a short period of time when you have that time of the season of the year. The one thing you have to understand that site versus source emission. So once you are using a gas boiler, you are burning the energy or the fuel on the site, and because of that, you have emission on the site. If you are using the electric, then maybe that electric will produce somewhere and transfer to your facility, and by producing that electricity, any fuel was used or burned, so it has their own site emission. I have like two comparison here from Ontario and Nova Scotia. You can see the Ontario, our electricity generation per kilowatt hour is only 35 grams of carbon dioxide emission. As compared to on the other side, if you see, Nova Scotia is 660 grams of carbon dioxide emission per kilowatt hour energy produced. Why? See at the bottom, the energy mix they have. Nova Scotia is mostly producing their energy from the coal. In Ontario, we are producing more from hydro and nuclear. It's a big portion of the electricity. And because of that, you see the two energy emission from the carbon dioxide. In terms of natural gas, generally we range from 186 or 190 or 180 grams of CO2 emission per kilowatt hour for the same amount of energy. So these are the two comparisons from gas and electric. And electric also, what is your source and how you're getting that electricity. Let's see an example of if we are producing 100 gallons of water from 40 degree supply from city water to 145. So we will be required 25 or 26 kilowatt hour of energy to raise the water temperature. If I'm using the first case as a condensing boiler, maybe it's like 90 or 95% efficient, then I will require about 28 kilowatt hour of energy to get this 25 or 26 kilowatt hour because of that efficiency loss. I'm just making this is our baseline and comparing with the other solution. If you have the older boiler with 80% efficiency, then you will have consuming more energy of 32 kilowatt hour. And if I had the third case is the electric boiler, for the simplicity, I will assume that electric boiler is working on 100% efficiency. And because of that, it will provide the 1 kilowatt input and 1 kilowatt output, and I can get 26 kilowatt energy consumed. And the last thing is the air source heat pump. Especially for the GTA area, the average annual temperature is like 47, 48. And out that temperature, the COP will be range 2 or 2.2, and you will consume less than half energy. So if you can see from 25 from electric, I'm using 12 kilowatt of energy for the same amount of water produced. In the worst case scenario, if the air source heat pump is working at minus 20 and my COP will drop to 1.4 or lower, still my energy consumption, and if you see the orange bars for the CO2 emission, we can still reduce. So as compared to gas to electric, it's like 83% reduction from in terms of, you see the energy consumption here, from an electric to heat pump, it's like 650, more than 50% reduction in terms of the electric consumption. So the both energy consumption is reduced, and also your carbon emission also reduced with the use of those electric heat pump, even with that lower efficiency. In the most period of the time when you will be using those electric heat pump, they'll be working at a higher efficiency of 2 or more, even up to 4. So on average, that will be much, much higher than 2.2. So you can expect that your energy consumption and your carbon emission both will be reduced up almost 50% or more. In some current studies, they find that especially where the older system was available with the natural gas, it was amount to even 60 or 80% or more. So that's the end of my section, and I'll hand over to Tyler for the next portion of.
Hello, everybody. Hello again, I should say. Rizwan, can you hear me okay?
Yep.
Okay. Yeah, so moving on to my portion of the presentation today. So as we mentioned earlier, Rizwan took you through, I guess, all of the motivating factors for why we might look to decarbonize a domestic hot water system, whereas I'm going to speak a bit more about the technology and how we might implement that on a given project. So I know most of you are already well versed in how heat pumps work, so I'll keep this portion of the presentation brief, but the same core principles apply to water heating. Rather than creating heat, a CO2 heat pump water heater extracts energy from the outdoor air, compresses the refrigerant, and efficiently transfers that heat to the water through a high-performance heat exchanger. The result is reliable hot water production, even when conditions outside are less than ideal. The efficiency advantage comes from this process, as Rizwan mentioned a bit earlier. So for every kilowatt of electricity consumed, several kilowatts of heat are delivered, meaning the COP is well above 1 in most conditions. This efficiency directly translates to lower energy use and fewer emissions, supporting building decarbonization efforts. CO2 heat pumps commonly use monoblock design, and multiple units can be installed as a modular array to deliver the capacity needed for large and high demand buildings. So a key differentiator of these systems is the CO2 transcritical refrigeration cycle. CO2, or R744 as most of us know it, is leveraged to achieve those high water supply temperatures. As Rizwan mentioned, up to 80 degrees C or 176 F in most cases. And that's because in this supercritical state, that CO2 refrigerant, or R744, it behaves both as a liquid and a gas. So this supercritical fluid has a very high thermal conductivity, and that allows for the heat pump to efficiently transfer that energy to our water loop for significant temperature lifts. So that's how we achieve that high delta T that Rizwan was mentioning. So beyond just the refrigerant, modern units are designed with reliable compressors and advanced controls that can handle high pressures and adjust to changing building demands throughout the year. So the end result is consistent high temperature hot water for domestic or commercial use, all while helping to reduce those emissions from the building in a meaningful way. So just to take a quick walk through the core components of a high lift CO2 heat pump water heater, what you would see here would be a monoblock QHV model offered from Mitsubishi Electric. Within this chassis, we're housing all of the common heat pump elements, like the inverter-driven compressor, outdoor coil, as well as an internal circulating pump for the primary fluid loop. Inside of the system, you'll also find a twisted spiral gas cooler. This is a heat exchanger that's unique to this particular CO2 heat pump, and it's specifically designed to work with CO2 in its supercritical state, which maximizes how efficiently the heat gets transferred from the refrigerant to our water loop. This unique component is one of the reasons CO2 heat pumps can deliver such high water temperatures at a very high delta T, sometimes over 50 degrees Fahrenheit, or up to 100 degrees Fahrenheit in some cases, all within what I would say is a relatively small footprint for that outdoor chassis. So just looking quickly at the topic of low temperature performance, I'm sure a lot of the common misunderstandings are still out there. Even in 2025, there still can be some fear about using heat pumps in cold climates. But I would like to highlight the fact that most modern systems have overcome these challenges. Many commercial grade heat pump water heaters now perform very well at very low outdoor temperatures, thanks to technology like the flash injection circuit that we see here. When running a heat pump at an extremely low outdoor temperature, there's often not enough cool refrigerant gas returning to our compressor to properly cool its internal components and manage the heat generated during compression. This is where this flash injection circuit comes in. It works by taking a portion of our subcooled liquid refrigerant and precisely metering it directly into our compressor. This extra injection helps cool the compressor windings and allows the system to maintain its high heating capacity, even when the temperature drops well below freezing. And as you see here, for this operating curve for this particular machine that we're looking at, you can see that we're still able to achieve full capacity down as low as 2 degrees Celsius. So I think this is an answer to a lot of those common misconceptions out there. Okay, so moving on to, I guess, plant design and how a plant loop might look for one of these systems. Let's take a quick look and a walkthrough of a typical plant piping schematic for a system using these CO2 heat pump water heaters. You'll see a couple of modular monoblock heat pumps piped in parallel, each equipped with its own internal pump. Heat is transferred to the building's domestic water loop via a double wall glycol to water plate heat exchanger, which provides that code compliant separation between our glycol mixture and the water. Another thing that you'll notice here is if you take a look at our cold water inlet, we're bringing domestic cold water directly from the city and heating it to a temperature from a single pass through these highlighted heat exchangers. So as Rizwan mentioned, and as I've mentioned a couple of times, we're taking quite cold water from the city. We're managing that at a very high delta T, high lift, and we're heating that directly to our storage temperature that's required for our building. So on the secondary or load side, we see some variable speed pumps that are used to match the primary flow and delta T This is critical for maintaining that system efficiency and proper heat transfer across that heat exchanger. And next is where you might notice a slight deviation from a traditional domestic hot water loop. As you see, our hot water storage tanks are installed in series to promote stratification throughout the tanks. I'll get into more of how this all works in a couple of slides now. And then next we have a swing tank or temperature maintenance tank, which is also an item that's commonly included to manage recirculation from the building. And then we have temperature probes throughout the system, and those are going to ensure precise on-off control for optimizing efficiency, comfort, and system longevity for our heat pumps. Okay, so just looking into some of the key considerations for some of the ancillary components that I just discussed. Each one of these components plays a key role in efficient decarbonized system operation. First, our heat exchangers, they should be rated for domestic hot water. We need to ensure that they're sized for peak load with minimal temperature drop across that heat exchanger. For systems that are using glycol as a method of freeze protection, we need to make sure that that heat exchanger is compatible and rated for use with glycol, as well as the proper derating factors need to be used when selecting the heat exchanger. Our pumps also need careful selection. The secondary pump should be sized to match the flow rate and the delta T of the primary side for balanced system operation. Because our low recovery, high storage systems generally provide lower flow rates from the internal pumps, it's important to select variable speed secondary pumps that can accurately manage this range. Using a variable speed pump not only ensures balanced performance, but it also helps manage fluctuating demands and improve overall system energy savings. And then lastly, getting into temperature sensors. Most manufacturers allow you to choose either their provided temperature sensors like we offer from Mitsubishi Electric, or sometimes there are compatible third-party solutions. But what really matters is planning for sensors in all the critical points throughout your circuit. Well-placed thermistors support accurate control of the heat pump, effective tank charging, and reliable system diagnostics, ultimately driving both dependable operation and that energy efficiency that we're all interested in. So as Rizwan mentioned earlier, many CO2 heat pump water heaters follow a low recovery, high storage approach. Because these heat pumps don't recover as quickly as a conventional boiler, large storage volumes are needed to meet that peak demand and support continuous decarbonized operation. As Rizwan mentioned, we're always looking to follow our HRAI or ASPE guidelines to size these tanks. So you avoid short cycling, prolonging that compressor life, and boosting that system reliability. Another aspect that we want to consider is for a lot of these low recovery, high storage systems, we're looking to use vertical configured tanks. In the example we see here, we've got multiple tanks connected in series, and we're looking to promote that laminar flow and stratification within these tanks. Another thing we need to consider is to plan for dedicated ports for our temperature sensors to ensure precise system control and water quality. Next, we'll look at temperature maintenance and the role of our swing tank. So temperature maintenance, as Rizwan briefly mentioned earlier, it's a key strategy for reducing heat loss in domestic hot water systems, especially in larger buildings with long recirculation loops. For those of you that work with high-rise multi-unit residential applications, standby losses can be significant over the course of a day, as a lot of us know, and throughout the night. That's where a swing tank or temperature maintenance heater comes in. Its primary role is to handle these standby losses by reheating the return circulation water without mixing in that main storage tank. This is going to preserve our thermal stratification. It's going to keep our main storage hot and will boost our overall system efficiency. Sometimes the swing tank can also double as a backup heater using an electric or a gas element if extra capacity is needed throughout the system. In those cases, it's typically connected in series with the main storage and sized for the building's full hot water demand. If it's just addressing recirculation losses, then it can usually be piped in parallel and sized only for the lower flow of the recirculation loop. So next we'll look at a couple of examples of how one of these CO2 heat pump water heating systems might work on, I guess, a high level. So we'll take a look at the flow path of our water through our plant loop. So in this scenario that we're looking at here, the heat pumps are actively generating hot water, but there's no actual hot water being consumed throughout the building, as you'll see on the hot water supply side. Here, all of our produced hot water is directed directly into our storage tanks, charging them, if you will. Our storage tanks, a lot of the time, in these low recovery, high storage systems, they can be looked at as thermal batteries, if you will. So in this scenario, we're charging our thermal batteries, so we're charging our storage. So all of that hot water that we're producing from our heat pumps is directly charged into those storage tanks. So there's plenty of supply available for upcoming peak demand. Sensor data and controls ensure that the heat pumps stop charging when we meet our tank temperature set points. Next, we'll consider this scenario where there's simultaneous hot water production as well as usage. The heat pumps are actively running and water is being consumed out in the building. And our hot water is immediately directed from the system to meet that building demand. This real-time supply draws down our stored hot water while the heat pumps work continuously to contribute to the instantaneous demand as needed, which is resulting in effective supply temperatures during peak periods. Once our hot water production from the heat pumps outpaces the demand that might be in the building, so at the tail end of our peak demand period, the storage will begin to be recharged. So one of the key concepts here to wrap your head around here is that the flow path through our storage tank, through these stratified tanks, is capable of reversing flow depending on the operating conditions out in the building. And then lastly, I'll show you the opposite case. So in this situation, the heat pumps have run, let's say, for that extended period overnight, like Rizwan mentioned. So we've had 16 hours of operation. We've started out with charged tanks, and then there has been a peak demand period that has come up, let's say, first thing in the morning when everybody in the building is taking a shower. So rather than operate the heat pumps right away during that peak demand period, the proper sequence here would be to deplete or draw down that hot water storage from our storage tanks so that we're using as much of that hot stored water as possible. So in this example, our building occupants are using hot water, but the heat pumps, they have been staged off because they were previously in thermal off, let's say. They charged the tanks. As our stored water is drawn down, the tank sensors throughout this circuit, they're monitoring that depletion of our hot water. Once the storage drops to a pre-programmed threshold, our controls will activate the heat pumps to recharge those tanks once again. This is one of the reasons we usually like to highlight why proper sensor placement and control strategies are so important for that reliability and consistent hot water supply out into the building. So just to take a quick closer look at control strategies with regards to sensor placement. With these low recovery, high storage heat pump systems, we're almost always working with vertical stratified storage tanks, as mentioned. That makes it especially important to monitor the level of hot water within each tank we see here. Placing temperature sensors at strategic points gives the system the information it needs to properly stage our heat pumps on and off, managing that tank charging and maintaining our temperature across the plant. So dialing in the placement of these sensors not only supports consistent hot water delivery and energy efficiency overall, but it also helps the system rely on the heat pumps in hybrid applications as much as possible, which also aligns with those decarbonization goals. So to take a more granular look at our control strategies using different sensors, the first example we see here is a 3-sensor method, we would call it at Mitsubishi Electric here. This is generally the most straightforward type of control. In this approach, 3 sensors are installed at different heights within our main storage tank. The on or the start trigger for the heat pump occurs when the stored hot water is being drawn down and replaced with that cooler city water signaled by our upper sensor. The off or the stop trigger point is when the lower temperature sensor detects that tank is nearly full and recharged with hot water at our set point temperature. Although it doesn't offer quite a flexible control, it's a practical, efficient choice for some of those more simpler projects, maybe with one module installed outdoors. Next, we're looking at our six sensor control. This method offers much greater flexibility and precision in how we operate our heat pump system. With 6 temperature sensors positioned at different points throughout our storage tanks, we can really fine tune when the system turns on and off based on actual conditions and some of those seasonal changeovers that we know very well here in Canada. So this flexibility is especially valuable for projects where the heat pumps are sized to meet, like Rizwan said earlier, to meet our full capacity on the coldest design days, like -19 at Pearson Airport, as those of us in the GTA know. Once those outdoor temperatures rise, though, in the summer, the same equipment suddenly becomes oversized or has much more capacity than is actually needed at those warmer temperature months. So our system efficiency, or our COP, can drastically improve with those warmer ambient temperatures. So things like the 6 sensor method, we can leverage those to adjust our start and stop points throughout the system. For example, in the summer, we can allow more of the storage to be depleted before giving the heat pump the on signal, which means for longer run times at lower frequencies and less short cycling when we have that additional capacity. Now, in the wintertime, we can set the system to recharge sooner after less hot water is being drawn down, making sure that there's plenty of time to recover the storage between those peak usage periods. This type of control, it not only improves efficiency, but it reduces our cycling, on-off cycling of our compressors. So it helps us get the most out of the heat pump's operating range. Just quickly looking at different operating modes for this particular QHV system that we've referenced here today. Most manufacturers, they do offer several different operating modes in their CO2 heat pump water heaters, giving operators flexibility to adapt to changing building needs and conditions. Here we'll walk through a few examples of one of our own heat pump water heating units. Like I mentioned, QHV is our reference point here today. So first one we see here is our maximum capacity mode. This setting runs the compressor at full output, which is ideal when there's a sudden spike in hot water demand, and you'll need that rapid tank recovery. Think early morning in a hotel or a gym just after rush hour when we have the most consumption. I'm getting the 10-minute signal here, so I'll try to leave lots of time for questions. And then generally, a lot of manufacturers will also offer energy saving modes. These modes will intentionally limit the system's maximum output, especially when outdoor temperatures, like I mentioned earlier, are quite mild in the summer months, but the demand is relatively low throughout the building. So by operating at a fixed or reduced capacity, the unit can deliver excellent efficiency and keeps those operating costs and carbon emissions in check. So in terms of installation considerations for our cold climate here in Canada, there's a few different strategies that we usually see leveraged on a lot of our projects here in Canada. When installing these heat pumps in cold climates, it's important to consider these provisions for freeze protection and long-term reliability. So for systems that are not using glycol in the primary loop, adding insulation and heat trace to our exposed piping can be an effective way to guard against freezing within that primary loop, especially on those outdoor runs between the outdoor unit and the building. We're almost always seeing insulated pipes on our external, but sometimes heat trace as well. A lot of the modern systems today will use automatic pump recirculation, which helps keep water moving throughout our heat exchanger and lowers the risk of ice formation in our heat exchanger when those outdoor temperatures drop. It's also mandatory for most manufacturers to install the outdoor units above local snow grade. making sure there's plenty of room for airflow, drainage, service access, because these are systems that will basically always be running in heat pump mode. We need to be aware that there will be periodic defrost cycles required in those colder months, usually between, let's say, 2 degrees Celsius and -5, where we're still able to have very cold but humid air in our outdoor space. We need to offer provisions to allow that system to defrost and for that water to drain away from our unit. So lastly here, we'll just look at some of the lessons learned that we've acquired over the years from the field. Every project teaches us something different, whether successes or from challenges. One of the common issues we've seen for a lot of these CO2 heat pump water heating systems is insufficient hot water supply out into our building, which often traces back to poor stratification in the storage tanks. And what we'll see is that hot and cold water get mixed together, especially due to how the recirculation lines might be connected to our, I guess, hot water storage or our plant. When that hot and cold water gets mixed together, it can disrupt the thermal layering that's essential for efficient operation. So if that recirculation is returned too high or in the wrong place, it can blend the warm water with the hot supply, and it makes it that much harder for the system to maintain the right temperatures. So just something to keep in mind. It is absolutely crucial how these storage tanks are configured and how our domestic cold water supply and hot water supply out into the building are connected to these tanks. So that is a bit about it from my side. So just to wrap up, the push to decarbonize domestic hot water is driven by energy savings, emissions reductions, and the urgent need for sustainable buildings. So we see success starting with proper system selection, sizing, and application of these heat pumps, particularly the CO2 air source models that we've referenced here today. So well-integrated controls, again, as a reminder, thoughtful piping, effective temperature maintenance, and solid freeze protection ensure you reach your energy and decarbonization goals, while reliable installation and proactive maintenance delivers that lasting value, especially in our Canadian climate here. So yeah, that's it from my side. Thank you very much for all of your attention here today. And we have about 6 minutes to field any questions that there might be out there.
Well, I mean, we can go longer if you guys want to kick around, but we have 3 questions. I think we can do it.
Sure.
Let's dive in. Now, I'm going to read them verbatim, hopefully, and if we need any clarification, we can ask for it. But first one is, what kind of D rate would you expect for defrost? Are there any strategies in place within the heat pump to provide continuous heating during defrost, i.e. split condenser coils, rotational defrost, and multi-module installations?
So I would say that a lot of manufacturers, they offer strategies to combat the losses that you might see during defrost mode. Every manufacturer is going to have a different strategy to manage these things. So one of the things that we use here at Mitsubishi Electric is prior to initiating a defrost sequence, the system will actually temporarily work with a boosted capacity. So we'll ramp up our pump, ramp up our compressor, and drive more heat into our loop prior to a defrost sequence, and try to balance out those losses as much as possible as we go into defrost. Yeah, like I said, every manufacturer has a different strategy, but that's one of the things that we do here at Mitsubishi Electric.
Thank you so much. Another question for you. Is it recommended to use dedicated glycol/water heat exchangers for each monoblock HP as shown, heat pump? Or is it okay to pipe all heat pumps to a single shared heat exchanger sized appropriately?
I hate to duplicate an answer here, but again, every manufacturer is different. The QHV model that we referenced here today, it's a requirement from our side to have one heat exchanger per QHV module. And the reason for that is because we have an individual pump output from each outdoor unit. So each outdoor unit is responsible for flow matching on either side of its dedicated heat exchanger. And I think the other part of that question was, is glycol recommended in all situations? That really depends on what the designer is comfortable with. If the designer is okay with implementing some sort of heat trace when the ambient temperatures drop quite low and our systems are off, that can be acceptable. But one of the things to consider is that that heat trace will likely need to be on backup power if it's used. So there are a few other factors to consider there. So I think from what we've seen, the most common form of freeze protection is glycol. So a lot of the CO2-based heat pump water heaters are approved to use glycol solution. So that's probably the most common one that we see.
Thank you, Taylor. One last question. Based on my experience, most designers and systems don't properly design a tank system that achieves good stratification due to pipe connection configurations, higher than expected flow rates in reality, high turbulence, etc. Can you please recommend any storage tanks with internal baffles or diffusers? Cheers.
Yeah, in terms of specific brands, I would say it's tough to say, but honestly, all of the main tank manufacturers that we've seen, they offer some sort of diffuser or baffle accessory that can come pre-installed when the equipment is selected or when the storage tanks are selected. So I think, yeah, that's one of the things that definitely needs to be flagged when those storage tanks are being selected. Is we need to make sure that I guess the distributor that's offering these tanks or walking through the selection with you, it needs to be flagged that this is intended to be a stratified tank connected in series. So we need to have relatively slow laminar flow through those tanks. And ideally, things like baffles or diffusers are included to promote that stratification. So in terms of specific brands, tough to say, but all of the main manufacturers of tanks out there offer that type of solution. I do know that.
Thank you so much, Tyler. Those are the questions we have for now. Do you have any contact information you can quickly throw up there if anyone needs to reach out?
Yes, absolutely.
Great.
Let me figure out how to share my screen again here.
No problem. Well, it's already being shared.
Okay.
Yeah.
Can we add it into our Q&A section?
Yeah, you know what? If you could just say it on the video and add it into the chat, that'd be great. I just like to throw out contact information at the end there, but since we are up against 1 o'clock, I think we'll call it there. Thank you so much to the both of you for being with us. We've got emails in the chat there, and we will probably see you guys again. You guys are a regular feature on our webinar, so thank you for that.
Thank you.
Okay.
Thank you
Thank
so
you
much.
very much for having us.
Thank you, everyone, for attending. Thank you. Have a good day.
Talk to you soon. Cheers. Bye-bye.